Right.
So good morning. Good morning. Can you hear me, Jorrit?
Yeah, can you hear you?
Can you hear me? Yeah. So I'm Matthias Stauderer. I will be chairing the session. Welcome everyone. Welcome everyone for the Thursday morning session of this workshop. And the first online speaker this morning is Jorrit Kruthoff from, I believe, Stanford, on TBar and holography, a status update. Yes, the Zoom stage is yours.
Yes, thank you. Thank you a lot, Matthias, for the introduction. For me, it's actually evening. It's not morning. It's like 7 p.m. here. I'm in Chicago right now. And yeah, today I would like to discuss a little bit, because I saw on the program that most of the talks are related to TBar and the relation to integrability and sort of what people call the non-holographic sign, or maybe some people call it the good sign or the only sign that makes sense. And I would like to talk a bit about the application of TBar in holography and the proposal by Verlinde that the TBar deformation corresponds to holography at finite cutoff. So I'll discuss a little bit of that, and please, like, if you have comments or questions, please just chime in. I made it into a more discussion type talk than like some result-based talk. So if you have any comments, questions, like please, or discussion points, please feel free to interrupt. So the first part will just a brief recap of what the proposal of finite cutoff holography and its relation to TBar is. And this works in any dimension, although in 2 dimensions it's the most rigorous, and 1 dimension as well. Now in holography, the usual way that we discuss holographic correspondence is by putting Dirichlet boundary conditions on our fields on the boundary of ADS. So the boundary of ADS is here in black, and it's at R equal to infinity. So this is at R in some Pfeffman and Graham gauge, for instance, this would be at R to infinity. And we fix the metric on the boundary up to some conformal factor. And the duality then says that, okay, this field theory is living on this metric that I fixed on the boundary, and in the bulk I have some calculation that I want to do, and in that calculation I have certain boundary conditions that I put. Now the idea of TBar is to slightly change that, that dictionary between the bulk and the boundary by, instead of putting the Dirichlet boundary conditions all the way at infinity, to put them at some finite radius. So at a radius related to some deformation parameter that I've got to write here. Let me write it. So the radius at which I want to fix the metric is given in this way, in terms of a dimensionful parameter lambda, and this lambda will be, the proposal is that this lambda is related to a certain coupling of an operator in the boundary. And as Verlinde, Metzey, and McGough showed, is that this parameter lambda couples to the TBar operator, an operator that was studied by Zamolodchikov. And in general dimensions with a flat boundary, this operator looks like this object in square brackets. And so when d is equal to 2, I recover the usual TBar expression. And you can extend this to other dimensions and you'll get some expression like the one I've written here. And well, the proposal is a bit more than just saying that, oh, I just turn on the coupling for this particular operator. It's actually more like a flow equation, and that we deform the boundary action or the putative dual in the bulk every step by this operator. So here this T now depends also on lambda. So this is some non-trivial flow of theories parameterized by lambda. Yeah, so that's the main proposal, and that gives a deformed dictionary, so a change in the dictionary. For instance, the deformed dictionary is actually the usual the obvious generalization of the one that we have at infinity, where the only difference here is that instead of having R to infinity, now you have some finite RC, and that RC is related to the coupling constant in the TBar theory. There's another, should mention here also that there's another way of thinking about the TBar deformation, as advocated by Monica Guica and Ruben Montan, is that you can think of these Dirichlet boundary conditions here at some radius as some complicated, well, not very complicated, but sort of balanced mixed boundary condition at infinity, which is such that you get the Dirichlet boundary conditions at some particular radius. Okay, so those are sort of the two ways of thinking about it. I will mostly take the first perspective, where there's a Dirichlet wall, and I forget about everything outside that wall. The nice thing about this deformation in any dimension is that you can solve it non-perturbatively in the deformation parameter lambda. So in particular, in 2 dimensions, of course, we can solve it exactly by using this factorization property of Zomolodchikov. But in higher dimensions, this is a bit more complicated because this factorization property is not does not hold anymore in that case. But what does hold is if you have a large N CFT, so you start off with a large N CFT on the boundary, or as your initial theory, you could look at states in which you have large N factorization. And for those states, you would have the factorization property. You can solve again the spectrum for the spectrum non-perturbatively in parameter lambda, and you'll find some expression like this, which just has the same functional form as the expression that we know and love from the 2D example, the 2D boundary example. But there are some factors of D here and there. So and here I should mention that the boundary topology is just a torus with sides L. So I just compactified the boundary. You can also do this for the sphere, if you have a boundary that's the sphere or hyperbolic space or things like that. And well, this formula will get a bit more complicated in the same way as the bulk geometry becomes more complicated. It's just a reflection of the duality. The fact that these energy levels become more complicated is also related to the fact that the deformation itself, the operator itself, becomes more complicated.
Sorry,
so
could you clarify the sign of the lambda? So this is, can you remind me of the like a good sign or bad sign, like depending on positive or negative of the lambda? This one is.
So here I'm taking lambda to be positive. Yeah, so lambda positive for me is the one that will have a complex spectrum at
I see.
At higher energies, this will become complex. Yeah.
Okay,
yeah.
Thank you.
Yeah, thanks for the question. So in particular, also this relation between the radius and lambda is given in this way. So this only makes sense when lambda is positive. Yeah. So yeah, I said already that for DS2 we can get an exact answer. Or
Jorrit,
yeah.
How do you get this quadratic equation for the energy?
This equation?
Yeah. Well,
so this can be so you have the large N factorization that you use in this expression. So this becomes an expression for the energy. This can be converted into an expression that looks like this. So d lambda of E is again some combination. I don't know by heart. There's some factor of D that I'm definitely going to mess up. But there's this flow equation for the action you can convert in a similar way as Verlinde does, for instance, in his paper. You can also write that down in this higher dimensional case. And you can solve it, and then the solutions are given by this expression.
okay.
Yeah, like things that you use here, right, are like that you're in these I mean, in particular, these energy eigenstates will be will have large N factorization. So you can write T tau tau is some energy density epsilon. And then TXX expectation value is again like the energy derivative of the energy respect to the volume, right? It's like the pressure. So things like that you use to derive this expression. Is that okay?
2D case is okay, but the higher dimension case, how can you generalize like a TXX and TYY, and there are more components in the higher dimension?
Yeah. So there for in that case, so TII, in that case you can generalize, but here I've taken this torus to have the same sides. Okay, so TXX is equal to TYY is equal to TZZ and whatever other coordinates you have, and it's equal to dE d volume. So this is really dE d volume. And if you have a sphere, then the stress tensor also has a particular form, and there's really only one component, I think, that you need to
Maybe Tij is just some zero or something, right?
Yeah, that I've taken to be zero here. Yeah, Tij, sorry, I should have mentioned Tij. Here I've taken to be zero, but you can also generalize this expression when you have non-zero momentum or angular momentum on the boundary. Yeah, so that would correspond to a rotating black hole in the bulk, for instance, or some boosted guy. Yeah.
I mean, how does large N come in here?
Because of the factorization. So this if I want to calculate the energy, what I'm doing is taking an expectation value of the entire thing. And similar as in the 2D case, right? You also have this factorization property that's being used to reduce this composite of the expectation value of this composite operator to a product of expectation values of one-point functions of t.
So that's kind of an effective action. It's not really the action, and it's kind of an effective action then?
Yeah, it's just an effective. Yeah, that's right. It's an effective.
Okay.
Yeah, it's far less precise in higher dimensions. Yeah, this only makes sense at large N and within some effective description. All right. Now, the other thing that of course happens in this case where we have in the relation with holography is that the spectrum complexifies. So the high energy spectrum, if I take some high energy state, then there's a certain lambda for which this complexifies. So this expression, because of this minus sign here and lambda being positive, this will go complex when lambda becomes when lambda is non-zero and the spectrum is just all the way to infinity, and this will be complex. And well, that's maybe a weird thing, and often the reason why this whole sign is not discussed, but it's consistent with the bulk. So in the bulk, that means that the actual cutoff surface now, so there's these states describe black holes. So we have a black hole in the bulk, and when the cutoff surface goes inside the horizon, that's precisely the location where this spectrum complexifies, and GTT in the bulk changes sign. So that's precisely why you get this. And because one of the big questions out there still in this whole TBar relation with holography is how we can make that. Can we make that work? Is there a specific way why this is, how we can cure this, or whether we need to cut off the spectrum in some artificial way, or whether there's a more natural way of thinking about it. Final thing I want to mention, but it's not, I'm not gonna delve into that more, is that we can also include matter. So besides, so I just talked about putting Dirichlet boundary conditions for the metric here at some radius, but you can also include, say, a scalar field or some gauge fields in the bulk, and you can then say, okay, I want to also put Dirichlet boundary conditions at that same radial slice. And you can convert that back to what that would mean in the holographic, in the field theory, and what kind of deformation you would need to add in order to realize that. And that will be much more complicated than just this guy, but it can be done. Let's see. So that's mostly what I wanted to say about the higher dimensional case, and then I want to move on to the 1D, the quantum mechanics case in the relation with two-dimensional gravity. But at this point, are there any questions or comments?
May I ask a question? So here you generalize the finite cutoff in the higher dimension. What about the 2D, and you, instead of the constant R surface, if you consider like arbitrary surface, is there a way to generalize it like a usual, like a nearly ADS? It's similar to nearly ADS, but in this point of view, is there some way to?
I will discuss the 2D bulk in a minute. So I wanted to say some more things about that. Related to whether you can do constant R or maybe something that depends on the spatial coordinate. That you can do, but you have to make, it's more complicated because you would need this coupling lambda, you would need to make that dependent on your spatial coordinates. So this will be more complicated. It depends on where you are on the boundary. Say there's some angle here. Say we're in ADS, then you would need to make this lambda of phi, and then you would need to deform with an angular dependent TBar deformation in order to get something that's wobbly in the bulk.
Okay, thank you.
That's one way of doing it. Yeah, and I don't think this has been done, but yeah. Okay. So what I wanted to do is talk a little bit about the 1D TBar version. that I worked on with Edgar Shagulian, Andrew Rolfe, and David Gross. And well, there's various ways of thinking about it. The simplest way is to just think about it as a dimensional reduction of the 3D case. Although as a standalone, you can also think about it as a standalone problem. And in that case, the gravity theory that we will be discussing in the bulk is JT gravity. And so the JT gravity is a two-dimensional gravity theory that has an action that looks like this. And it has a metric, and the R here is the Ricci scalar of that metric. And phi is a scalar field called the dilaton. And this dilaton in the bulk acts as a Lagrange multiplier, and it sets the Ricci scalar of the manifold equal to -2. So that means that in this gravity theory, only hyperbolic surfaces contribute. So only R is -2. Then for, since we want to have a boundary where some quantum mechanics is going to be living, there will also be a boundary term. And this boundary term is there to make the variational principle well-defined. And the specific boundary term that I'm going to consider is this one. I think I forgot here to write some phi, so that's also there. I should mention that this first term is just a given short boundary term. And this -1 here is a counter term that I have included to make things well defined. The calculation of partition functions, etc., has a volume divergence, and this -1 is going to cancel that. All right. So that's the JT action, and what I want to do now is to consider JT gravity at finite cutoff. So I'm gonna consider this gravity theory and now put Dirichlet boundary conditions at some finite radius. Right. And the way to think about that, as I was saying, can be done using just the 3D theory and consider the zero momentum sector of that theory. That's a very simple way of just getting to the formulas that are there. So if you look at the spectrum, the deformed energy spectrum in the 2D TBar theory, and you set k is equal to 0, then you get an expression that looks like this. And it's this deformed spectrum that you would expect in the so the deformation that you want to do in the quantum mechanics should reproduce this particular deformed spectrum. And of course, now the question is, okay, how can we reproduce this type of spectrum? And so now I'm mostly talking.
Just one, I guess one question is that your previous formulas for arbitrary dimension, when D went to 1, didn't seem to obviously go to this kind of form.
That's right. So you take the 2D expression and you go to the zero momentum sector. Also explain a little bit more how the deformation is defined, but right now I just wanted to get a simple formula
okay.
Just from the 2D theory. Yeah.
May I ask a question on this formula?
Yeah.
And when lambda is large enough or for high energy state, the Hamiltonian in principle it's not Hermitian or
it's complex. Yeah, the eigenvalues are complex. Yeah.
And is there any problem in here? You base on here the derivation of the formula is based on the many like a good property of the eigenstate, energy eigenstate. But if Hamiltonian is not Hermitian, is there any like a problem to arrive this conclusion?
Well, I think you can still diagonalize it, but of course, this expression is not. There's definitely problems when this thing becomes complex. I mean, you can say, okay, it's not Hermitian, but I can still diagonalize it. That should still not be a problem. But I'll have some comments about this complex energies in a little bit. And so yeah, we can discuss more in a little bit.
Okay. Yeah. Thank you.
Yeah. Thanks for the questions. Right. So how to derive this formula? I gave you a very quick argument of going to the zero momentum sector in the 2D TBar deformed theory, because that's also the way in which the JT gravity arises from the 3D Einstein-Hilbert action. To understand why this is the correct deformation, one way of doing that is by looking at JT gravity, the bulk JT gravity, and doing a radial ADM decomposition in the bulk. And writing down the constraints that a wave function, so the Wheeler-DeWitt wave function, needs to satisfy. And there are certain constraints that need to be satisfied that follow just from diffeomorphism invariance. And the radial constraints, or the radial Wheeler-DeWitt constraint, you can write that down exactly in the in this JT gravity, and it takes this form. Of course, exactly. There's always in this Wheeler-DeWitt business, there's always the problem of operator ordering. There's some issues that are always present there, but there is a choice of operator ordering that that basically gives you the correct result. And you can also maybe discuss other types of operator ordering. But for a specific choice, the Wheeler-DeWitt equation takes this form. Here L is the length of the boundary, or the length of your radial slice, and phi is the value of the dilaton on that slice. So those are the two gauge invariant observables that you can have in this case. So the Wheeler-DeWitt equation is this, very simple, and you can solve it. And what you find is indeed this type of spectrum, and lambda is then related to the dilaton in some way. Another way to derive this deformation, or this particular spectrum, or and in particular the deformation in the quantum mechanics, is by doing a dimensional reduction of the 2D deformation.
Sorry, one question.
Yeah.
So this Wheeler-DeWitt equation is typically a second order and length derivative, right? It's only first order.
Yeah, so that's particular for JT gravity. If you work through the derivation, then you'll find that it has this particular form. Was there a way of thinking about that? Yeah, I think one of the reasons is that you have the coupling is like phi times r. So you have already this sort of mixed term in there, and then there's some particular partial derivative that you take, and then to write down the momentum dependent piece, you get the momentum of the dilaton conjugate to the dilaton times the momentum conjugate to the metric variable. So it comes really from the phi r in the action.
Okay, so it is actually a second order operator, but just mixed in derivatives with respect to L and phi. Okay.
Yeah. Oh, sorry. Yeah, I thought you meant that. It's still second order, but it doesn't have the DL square, if that's what you. I thought
Okay,
you meant.
that was my question.
Okay, good. Thank you. All right, so you can derive from this Wheeler-DeWitt equation. Another way to see it is to do a dimensional reduction of the 2D deformation. So first of all, the 2D deformation, the TT-bar operator satisfies a quadratic relation between the trace and the TT-bar operator. So this is a curious relation, but from this relation, you can find that what the 1D deformation should be. And so the 2D deformation has this particular form. And now let's consider setting t tau x to 0 in the 2D case. And then we're going to use this equation with t tau x to be 0 and solve for txx. So let's solve for txx, and we get an equation that looks like this. Then we can integrate out over the angular coordinates that we're reducing along, and you'll get a flow of the 1D quantum mechanics action that looks like this. And this flow of the action, of the 1D action, can be turned into a flow of the Hamiltonian. And so this flow of the Hamiltonian has a sort of peculiar form, but when written in terms of the Hamiltonian, this factorization property is just trivial. You get it for free. So in that way, you can think of this comment I made earlier that you can do any of these deformations and think about the factorization property just comes for free in this case. And so as a standalone problem, this 1D quantum mechanics deformation is very well defined. You don't need some extra ingredient to do the factorization and get all these nice properties that you have in 2D, and where those properties are non-trivial. But here this all comes for free. And a little bit later, I will talk about some generalizations of this particular deformations of quantum mechanics. Yeah, but let's keep that for a little bit later. Now, so we know now what the deformation is of the to get JT gravity at finite cutoff. It's a deformation that either we think about as a deformation of the action or a deformation of the Hamiltonian. But yeah, so what is the action that we would like to deform in JT gravity? So what is the boundary effective action? So in JT gravity, the boundary effective action is the Schwarzschild action. And that basically arises from integrating out the dilaton in the bulk. So that's set that the bulk scalar curvature R is -2. And then we can consider different, so say we're on the disk, we can consider different cutout shapes of the disk. And those different cutout shapes correspond to different reparameterizations of the boundary. And these reparameterizations of the boundary, they will show up in the boundary action. And so the action depends on those boundary reparameterizations. And if you work through the details, the extrinsic curvature actually of the boundary theory, so this expression I had written here before, this k-1, this k-1 precisely becomes the Schwarzschild as I take the boundary to be very large. I take the boundary to be very large. There are some fluctuations close to the boundary that remain, and the boundary action will be that of the Schwarzschild of the reparameterization. So this is the boundary action, and what I now want to do is consider the TT-bar deformation of this action, because the TT-bar deformation of this Schwarzschild action should be the effective action of the of JT gravity at finite cutoff. So this should, in a similar way as the Schwarzschild theory describes the gravitational dynamics in the bulk of ADS2 at infinite radius, the TT-bar deformation of this guy should describe the gravitational dynamics inside a finite patch of ADS2. And later I will, so I can mention now that you can also show this by just doing the Euclidean path integral. So you just compute the Euclidean path integral where you put Dirichlet boundary conditions at finite cutoff and calculate that that bulk partition function, and then you can see that it matches onto the partition function that you would get from TT-bar deforming the Schwarzschild theory.
So here I have a question. So
yeah,
in the TT-bar deformation, you have in previous slide you also have a Hamiltonian. So that Hamiltonian is generated along the like a boundary time, right?
Yeah.
And here JT gravity, how can you from the beginning, how can you define the Hamiltonian? Usually you in gravity you can consider the radial direction as time, and you can define the Hamiltonian and so on. So that Hamiltonian appear in the later is that Hamiltonian in the radial direction or Hamiltonian along the boundary time?
Yeah, it's the Hamiltonian along the boundary time. So this Schwarzschild theory you can also write in terms of in a more Hamiltonian way, where you introduce some phase space variables. You need because this Schwarzschild theory is higher derivative. You need more momenta to write down a phase space for this theory. But you can write down a Hamiltonian in that language. And that will be the Hamiltonian that you will be deforming.
Okay, yeah. You will show some detail, right? Or
yeah. I'll
I will wait.
All right. So yeah. So what's the partition function of the Schwarzschild theory? So what's my initial theory? The initial theory is given by the Schwarzschild theory, and the partition function at some finite temperature, which means a finite boundary length beta in particular. This partition function takes this form. So there's an e to the 1 over beta, and then there's an 1 loop term, which is beta to the 3/2, or 1 over beta to the 3/2. And if you do a inverse Laplace transform of this, you can find that the density of states of the Schwarzschild theory is a sinh square root e, and the spectrum is therefore continuous. And so this theory is a little bit it has a continuous spectrum, so it's a little bit weird. But this is very common in these type of theories dual to gravity, at least in this order of approximation. Now, so what I want to do is TT-bar deform this particular theory, and I can basically do that. So I have a non-trivial density of states, but the spectrum is not going to be, the density of states of the deformed spectrum is not going to change. The only thing that changes is the eigenvalue. So that's also a consequence of that I can write the deformation purely as a flow of the Hamiltonian. So, and if I evaluate this in energy eigenstate, then the deformed spectrum, the states will not change, but only the eigenvalues will change. So that, if you do that, then you can basically replace this energy here by the deformed energy. So that will be a simple expression like this. And so the deformed Schwarzschild theory is basically this integral. So the spectrum is it's the same still, but the energies are a bit different. What you can do, of course, is to go to new variables, a new E tilde, where you can go to E tilde equal to 1/4 lambda 1 minus 8 lambda E. So that you just get the usual Boltzmann factors, and then you get a change in the density. That's you can do this integral also exactly, and you get a fun expression that is this Bessel K2. And here you immediately see that this expression is complex. So as you would expect, so in particular this factor here signals that this thing is complex, because lambda here is positive. And this K2 for negative values of lambda is also complex. So this entire expression gives you something complex if lambda is positive. I mean, strictly speaking, this entire integral does not converge when lambda is positive. So you could also say, okay, what do I mean with that? You can say, okay, let's compute it for lambda is less than 0 and analytically continue. And then this is the expression that you get. Yeah, so that, yeah. Now this expression, this deformed.
May I ask a question? So
yeah.
when you do the analytic continuation, is it unique or there's some other branch like so if you said you go to the negative lambda and you do some analytic continuation, and is there some ambiguity in that analytic continuation so that you will maybe have a different solution? Or
yeah, so the one thing that's definitely true is that there's other branches that might contribute. Like the biggest problem is that this Bessel function is evaluated on its branch cut. So whether you analytically continue above or below the real axis gives you different answers. Yeah, that's I think what you meant, right?
What is the reason you choose this function? Like I mean, like if there is some ambiguity, then
right. What I'm saying here is that really this expression, like this equality here only makes sense when lambda is negative. Like this integral will not converge when lambda is positive.
Ah, I see. Yeah. Okay.
So really the expression that I wrote here only makes sense for lambda is negative. But okay. I'm saying that you can, if you want to, you can continue it to positive lambda. But yeah, I'll have some more to say a little bit later also about the relation with the complex energies. In particular, because these TBar deformed partition functions, they satisfy a certain, as I mentioned before, a radial Wheeler-DeWitt equation. And before I had written it in terms of L and phi. If you actually go to these lengths and these the value of the dilaton, they need to be renormalized in the usual way. And you go to the variables beta and lambda, this flow equation of the partition function takes this form. So this is a second order differential equation. And this is actually the dimensional reduction again of the flow of the 2D partition function. So if you do the TBar, there's this a paper by Aharoni et al. Where they derive a flow equation for the partition function. And this guy is just the dimensional reduction of that. It's like you said, tau1 equal to 0 and tau2 is beta, basically. All right. So the problem, as already people mentioned, is that when lambda is positive, this thing is complex, and well, this doesn't even make sense. So how can we cure this? Can we make sense of that? Now, one way to cure that is to look at this differential equation and try to solve it with a boundary condition that as I send the lambda to 0, I recover the Schwarzschild partition function. And I can try to find solutions that satisfy that boundary condition, for instance. So first of all, what you find is that that there is actually two different spectra that are consistent with this flow equation. Namely, you can have either sign for the square root. And of course, that we already knew also from the 2D TBar. So there's actually two different partition functions that you can consider that are still real. So for instance, I could consider these objects Z plus minus that I defined here, where I'm going to integrate the energies not all the way to infinity, but all the way to 1/8 lambda. So that's precisely the location where these energies go complex. So this is a lambda dependent cutoff. And then the integrand, you have some density of states here, which I will take to be the Schwarzschild. But I should mention that actually any density of states you can put here. So that's just a reflection that I can take any boundary theory that I want and deform it with this deformation. And then the Boltzmann factors are changed in this way, where, okay, now I have this plus minus for the different branches. Now, because of the lambda dependence of this cutoff that I put here, so this expression will now be completely fine. It will be finite and everything. It will not be complex. But because I put this lambda dependent cutoff here, it will not satisfy the differential equation anymore. Instead, what will satisfy the differential equation is the difference of these two. So I just have the usual branch where it's 1 minus the square root. And then I'm subtracting the Z plus, so with the 1 plus square root. And I need this minus sign precisely to cancel the two different boundary terms that I get for each of them. So Z minus gives me a boundary term here, and I subtract Z plus to get rid of that boundary term. All right. What you can also do is, well, I don't want to cut off any spectrum, and I just add to it the other branch. That will also be real. It would also satisfy the differential equation. But you sort of have a spectrum that has complex conjugate eigenvalues. Has complex conjugate eigenvalues. And the question here is that, okay, is there a holographic interpretation of either of these two proposals? So is there a holographic interpretation of Z hat of this guy with the minus sign, or is there perhaps a holographic interpretation of this Z tilde? And yeah, to me, it's not clear, but there is. One thing that is particularly confusing about this Z hat here is that because of this minus sign, the density of states will be negative. So this deformed Schwarzschild theory, and when you consider this difference, is actually complex, or has a negative density of states. That's of course not quite what you would want. So then maybe this Z tilde would be a better proposal, but yeah, then you would need an interpretation of this other branch, other solution branch as well. Right, so this one corresponds to this deformed spectrum here, matches nicely onto what we expect from from holographic, from the bulk. But for this guy, I'm not quite sure what that would mean holographically, because it sort of says that the bulk is then dual to 2 spectra, and maybe that's a correct way of thinking about it. But yeah, it would be nice to have some more evidence for that statement. Yeah, so as I already mentioned, there's more quantum mechanics sort of reasoning that I was mentioning, but there's also a Euclidean path integral calculation of this partition function, and then you also find this expression, or rather you also find this expression. So in that sense, you can derive it in different ways. Okay. Any questions at this point? All right, let me continue. So I wanted to discuss some generalizations. So if we consider a quantum mechanics, I think I made a mistake here. I realized later that I got this the other way around. So in quantum mechanics, the IR is actually much more non-universal. So there's, I flip this to around. I think this sentence should also be gone. Let's just get rid of all of this. This doesn't make any sense. Good. So in a quantum mechanics, the sort of logic, the Wilsonian RG type logic, that the UV is sort of rigid, is sort of so that the UV is very complicated, and flowing up the RG flow is okay. You can land, you don't know where you're going to land. It's very complicated. In the quantum mechanics, it's the other way around. So the UV is more rigid, and the IR is very very irrelevant, or relevant operators are very easy to write down. That's because the scalar field, if you have a scalar field in the quantum mechanics, has negative dimension. And so the examples of such deformations of the UV also, although they're sort of, the UV is sort of rigid, there's easy ways of constructing deformations of the UV by doing what we call the Hamiltonian deformations. So I take the Hamiltonian of my favorite theory, and I deform it by some function of the Hamiltonian. And an example of this was this TBar theory, this deformation of the TBar theory that I discussed before. And so there's a whole host of different types of deformations that you can consider. For instance, you could, instead of looking at ADS gravity, ADS2 gravity, you can consider DS2 gravity, and maybe consider not cut off in the usual radial direction, but maybe in a time direction, or you can slice the sitter, like look at the static patch of the sitter and look at sort of radial slices in the static patch, or in some other type of slices. One proposal by Eva Silverstein, Viktor Gorbenko, and Gonzalo Torova is a picture where it's a proposal where you start off with the usual ADS3 geometry, and you TBar deform. So you write ADS3 in terms of ADS2 slices. You deform all the way into the bulk, and then you turn on a different deformation to move you out of the sitter. So at any rate, there's different types of deformations that you can write down in quantum mechanics, and okay, it would be interesting to understand what the space of these deformations is. But yeah, I think in particular it would be more interesting to understand whether there are more general deformations in the higher dimensional case, and especially in two-dimensional case. And maybe one way to approach that is by looking at these integral transforms that people have been looking at. So the TBar deformation can also be thought of as taking your CFT and hitting it with some kernel and integrating over the metric of that the CFT is defined on. And this kernel now depends on the metric gamma and some other metric gamma prime. And there's an integral transform like this that you can write down in the case of the TBar partition function. But also in the higher dimensional case, you can also do this. In particular, in higher dimensions, this was done by Alex Bellin, Aitor Lukowitz, and Gabor Sarosi. And there have been various generalizations by Mazenk, Sony, and Fasu to generalize this type of kernels to the TBar deformation, or also for there's some ongoing work doing it also for Eva, Silverstein, and Gorbenko and Toroba's lambda 2 deformation. And the nice thing I think about these kernel methods is that, perhaps they form a better way of defining the TBar deformation, especially for this holographic sign, where the spectrum becomes complex. Perhaps you can deform the contour of this path integral here to make that well defined. And of course, you can think of more general kernels that, okay, maybe take your favorite CFT partition function and hit it with a particular kernel. Is there a way of mapping out what the different consistent partition functions are? Like, can I define a deformation by using this integral transform and get some sensible theory, or are there some non-trivial conditions that this kernel K needs to satisfy? I think that would be interesting to see if that can be done. Yeah, so yeah, that's really this point one that I was telling you guys about. Then this second point is just a way of studying that. You could look at how the spectrum gets deformed. Of course, that's a bit more complicated if you're in higher dimensions, because you can have momenta that also appear in your Boltzmann factors, and so that might be more complicated to run through your kernel to transform it. But all these things can be done for the TBar deformation. We know how that works, and well, you can change that kernel a little bit and see what type of deformation you end up with. And maybe you can also write down operators in the 2D theory that precisely correspond to that deformation. And those will also be exactly solvable deformations. And I think it would be very interesting to map out whether there are other deformations than just the TBar or these higher spin generalizations that can also be used. Right, I also mentioned number 3. Now, another direction is that this kernel, this integral, can be thought of as coupling the CFT, the initial CFT, to a worldsheet, a string worldsheet. So this partition function, you couple it, this theory, you couple it to a string worldsheet, and you can define the TBar theory as some sort of string theory. And that many people have done that. In particular, Alessandro Sfondrini has been working on that quite a bit. Now the point is that you can, although you can make it precise, it sort of only works in the winding 1 sector, or only in the winding 1 sector of the string is there a, do you get a match with the TBar spectrum? You can generalize it to other winding sectors as well. That's quite straightforward. But I think what's the nice thing about this relation with string theory, and this has nothing to do with holography at all, even in the case where we have the sort of good sign, so the sign where the spectrum does not complexify for some range in lambda, is that in the string theory language, at some point, right, at some point when lambda gets bigger and bigger, the ground state complexifies. And on the string theory side, that means that there is a tachyon in the spectrum. And I think this relation with string theory might be interesting in that regard, because you could answer the question, okay, what happens to the tachyon? What happens to the what happens after I tune lambda too big? And does this tachyon condense, or is this theory really unsensible? Or yeah, can we add some simple ingredients to make it happen, or to make it more well defined beyond that critical value of lambda? I suspect that probably that needs to include all the winding sectors, so that is another complication that you would need to overcome, or and that will also reflect the theory when you turn off the deformation. Right. Yeah, and then some final comment that this string picture also exists in the 1D theory, but then it's really coupling to a world-line gravity. So in that regard, it's much simpler. But again, these kernel methods are still there, and I think it would be nice to understand these kernel methods not only in 2D but also or not only in 1D but especially I guess in 2D. But there's more of those kernels that give you sensible partition functions. And that was it. Thank you.
Thank you. Thanks for the nice talk. Well, we had a lot of questions. Maybe there are some more. Yeah.
Yeah, I mean, can you say a little bit more about, you said, you know, the sort of the opposite sign of, I guess you call it lambda, didn't have this square root singularity. I mean, what was the string picture of that? Can you kind of summarize that?
Doesn't have, I didn't say anything about it doesn't have a string, and that it doesn't have the square root singularity. I just meant that
at some point, you know, you had the square root, but you know, for the sort of I guess what you can measure would be the negative sign of lambda. There is never becomes complex.
Right. So that's
somehow well behaved. So
right. Yeah.
Does that mean, well, there's no fundamental scale at that point? There's no like potential string scale. So, you know, I mean, what can you say about that case again? You said a few words about it, but I kind of missed it.
Right. Sorry. Yeah, I can. What I meant is that, okay, just the spectrum in that case, like if we look at the, so that will be, so lambda now is negative. So let me change sign. So let me just put a minus plus here. That's okay. And then we have 1 plus 8 lambda e here. So I'm looking at the K0 sector. So because if I turn on the momentum, that will only make things better. And what I said is that, so here the spectrum never complexifies. Is Andre still here? Oh, maybe hello? And Andrea, are you still here? I think
like we lost the connection to Andre.
Okay. Well, I guess the talk it's recorded, so maybe I can just
Yeah.
finish
Okay.
it.
Andre, can you hear us?
Yeah, I can hear you. Oh, I can hear you also, Andre. Yeah. Mhm.
Okay, yeah, sorry, I got disconnected there. Yeah, I mean, you had, that might, I don't know what you said, but my question was, with the sort of the wrong sign of lambda, there's no complex energies and.
Yeah, that's right. There's no so the way to see that is that in if I change, so here I've written down the spectrum, the deformed spectrum, with the sign of lambda flipped.
Yeah.
Okay?
So it has
this doesn't complexify, except
yeah,
for E less than 0. So for the ground state in particular.
Oh yeah, sure, yeah, right, okay, sure.
So
yeah,
this guy will.
Mm-hmm.
This will complexify after some critical lambda, and if in the string spectrum that manifests itself as the existence of a tachyon in the spectrum.
Mm-hmm.
And what I was thinking about that is that, okay, in string theory we sometimes know how to deal with tachyons in the spectrum, or sometimes we have tachyon condensation, or we and I think it would be interesting to understand purely from the string perspective whether there's a way of understanding this complex energy, whether the tachyon condenses and the theory maybe goes into some other phase.
But what if E was positive? Then you wouldn't have this this complexification. So
no, when E is positive, but if you calculate the partition function, partition function will be
so then you don't have any weird pathologies. I mean, what would be the interpretation? Like, it sounds like you wouldn't even need a fundamental scale in that kind of theory. So what would be the string interpretation, if anything?
You mean at very high energies?
Yeah, sure, yeah.
I mean, at very high energies, this is just a bona fide string theory. There's nothing pathological at high energies. Like this theory just have will have a Hagedorn spectrum. So it will not make sense beyond some temperature. But okay, those are the usual issues that we nevertheless have with these particular string theories. But the problem I was alluding to is that if you calculate a partition function, then you would need to include the ground state energy, and that guy just gives a complex contribution if lambda is too big. And my question was, can we cure that by studying the dynamics of the tachyon? And maybe we need to include some other ingredients, but perhaps from our intuition from string theory, we might be able to see what happens to those energies that have negative energy. Yeah.
All right. Thank you. Yeah.
Yes. Thanks for the question, Fred.
I think we have another question from a local participant, Mitsuhiro Nishida. Yeah.
Sorry. I also have a question about negative lambda. So
yeah,
in your talk, you explained finite cut holography with positive lambda.
Yeah.
And is there a holographic proposal for 1D TBar deformed theory with negative lambda?
Yeah, at the moment I don't have a holographic interpretation in that case, because this relation r square is roughly equal to 1 over lambda holds also in the 1D theory. So if lambda is negative, then r needs to be complex. And yeah, I don't know what that, yeah, I don't think there's a holographic interpretation in that case. Or at least I don't understand. I don't know what it would mean. but maybe there is an interpretation.
So I think two-dimensional TBar deformation with positive lambda can be studied, can be interpreted by using little string theory. And can you consider dimensional reduction from little string theory to study one-dimensional TBar deformation?
Yeah, I'm sure people. I'm sure you can try to do a dimensional reduction. Although I'm not an expert on that single trace story, so there might be issues in doing the compactification, but superficially, I think that okay, maybe that you can do, but I think even there are some complications. Yeah, there's even in that, even with the little string proposal, there are some complications. Like you can have time-like closed curves, something like this.
Thank you.
Yeah, thanks.
Okay, are there any further questions either from local participants or from Zoom participants? That does not seem to be the case, so I would like to thank Jorrit one more time for his very detailed and nice and pedagogical talk. Thanks a lot for joining us from Chicago.
Yeah, thank you. Yes.
And yeah, so you can clasp, maybe the microphone will pick it up.
Yes.
Please give him an applause.
Thank you.
Could you hear this, Jorrit?
Thank you.
Yeah, okay, thanks a lot, and good evening, good night.
Thank you.
Yeah. I think I'm gonna get some dinner now.
Yeah.
But
I should get some sleep, but
oh yeah, good idea. Good idea. Thanks for attending, and thanks for all the questions. That was great. Thank you. Bye bye. Organization is first few